Hi, good morning. I'm Wang. So today I will give a presentation about the carbon export through different mechanisms in the subpolar North Atlantic. So for the carbon export, it roughly involves two steps. The first step is to fix atmospheric CO2 into the organic carbon through photosynthesis, and this step often happens within the euphotic zone. And then in the next step, the organic carbon will be transported into the deep ocean through different mechanisms and maintain the ocean's uptake of CO2. During these processes, the POC fluxes is subject to respiration. So how much and how deep the organic carbon can be exported have important implications for the atmospheric CO2 levels. But the answers to these questions so far have much uncertainties due to the lack of observations. The recent advance in BGC algal flows has provided us a large number of observations and great opportunities to characterize the carbon export flux. The usage of bioptical sensors also makes the measurement of POC available. So here, for example, I use this figure to show the global distributions of the BGC algal profiles. And we can see that we totally have more than 200,000 profiles in the global ocean over the past 20 years. So this study purpose is to estimate the carbon export flux due to different mechanisms, as well as their effects based on the BGC algal flows. For this purpose, we divide the POC into two size classes. They are the large, fast-sinking POC and the small, slow-sinking POC. For the small, slow-sinking POC, we assume that no export at the base of mesopelagic zone, which is defined as 900 meters in our study. So given such a word column, the vertical integration of the small POC can be supplied by the total export from the upper layers due to different mechanisms, and the internal source, such as fragmentation, from the large POC into the small POC. The vertical integration of small POC can be also decreased due to the remineralization. So the temporal evolution of the POC inventory during two sampling steps can be represented by a partial derivative equation. And in this equation, the S represents the source, and this part represents the remineralization. So by resolving this equation, we can get such a formula to describe the temporal evolution of POC inventory during these two sampling steps. And then based on this equation and the observations at two sampling steps, we can estimate the source of small POC. So here is the equation for the source of the small POC, and it includes the total export flux and the internal source. We also notice that when the remineralization can be neglected, the source of small POC is equivalent to the changing rate of POC inventory. So this equation has been used in previous studies to approximate the carbon export flux of small POC. So the key of this study is to determine the remineralization rate and other parameters associated with the POC. For this purpose, we assume that the large, fast-sinking POC consists of two components, where the refractory part is approximate constant throughout the whole word column and is represented by these parameters in this equation. The nearby part attenuates in an exponential way. That means they have a constant sinking velocity and attenuation rate. So this exponential part of the equation can be also applied to the small POC. So for the small POC and nearby large POC, the attenuation rate is determined by the remineralization and fragmentation. And for the nearby large POC, the total attenuation rate is a sum of both. But for the small POC, it's a little bit complicated. The attenuation rate is modulated by the fragmentation rate and the ratio between two POC classes. And then based on this exponential equation, we can also estimate the attenuation length of the small POC and nearby large POC. So the attenuation length is the distance required for the carbon flux to attenuate by 63%, and is defined as the ratio between the sinking velocity and attenuation rate. We also have this equation of the attenuation rate of the small POC. So based on this equation, we can also derive a relationship between the small POC's attenuation length with the fragmentation rate. Then to determine the remineralization rate, we linked POC concentrations to the auction. So here is a budget of the subsurface auction, and by neglecting the phase advection and diffusion, the auction utilization can be represented by the small POC and nearby large POC. So we divide each float measurement into several 1-year segments, and we only use observations below the mixed-air depths. So as an example, this figure shows the vertical distributions of the auction utilization, and this black line is the mixed-air depth. So we will only use the observations below these black lines. This figure shows the time series of the auction utilization and the temporal integration of small POC and nearby large POC. So we can see that they are highly correlated. And to determine the remineralization rate, we tested a range for these two parameters by reporting the root mean square errors between the fitted and observed data ALU. Then we checked the BGC algal flows in the subpolar North Atlantic. So this figure shows the BGC algal flows, which measured both auction and POC. And this figure shows the available profiles. So we can see that we totally have 8 flows in the Labrador Sea and emerging sea, and we have 6 float segments which have a complete annual cycle. So here the complete annual cycle means that they have profiles from January to December. These 2 float segments are influenced by the float drift. So we will apply the above mentioned analysis to these 4 float segments. And next, I will show some preliminary results and use 1 float segment as an example for study. So this figure shows the vertical distributions of the large POC and the fitted line. So the yellow line represents this exponential equation. So based on this exponential equation, we know that the refractory part accounts for about 10% of the large POC, and the attenuation length of the large POC, of the nearby large POC, is about 270 meters. These 2 figures show the vertical distributions of the small POC and the relationship between their attenuation length with the ratio between 2 POC classes. So based on this regressed equation, we know that the remineralization length of the small POC, which means if we don't consider the fragmentation, the remineralization rate of small POC will be about 70 meters. And the fragmentation rate is about 1/4 of the remineralization rate of small POC. To determine the remineralization rate, we plot the root mean square errors between the fitted and observed ALU. So the optimal values for these two parameters are represented by these black dots in this figure. So for the small POC, it's about 0.05, and for the large POC, it's about 0.07. But here we didn't use these optimal values directly. Instead, we set some criteria to select a possible range for these 2 parameters. The first criterion is that the root mean square error should be inside this inner contour line, which means that the increase of root mean square errors from the minimum values should be lower than 0.1. And the second criterion is associated with the sinking velocity of large POC. So in this figure, the black dashed line represents the contour line of sinking velocity of large POC, and they are parallel. So for this float segment, we assume that the sinking velocity of large POC should be higher than 20 meters every day. So as a result, this table shows the range of these key parameters. And for example, we can see that the sinking velocity of small POC is between 3 to 5 meters every day. And for the large POC, the sinking velocity is between 20 to more than 30 meters every day. We can also notice from this figure that the root mean square error is more sensitive to the remineralization rate of small POC than that of the large POC. So that means the remineralization rate of small POC can be better constrained And this is a quite good news for us because to calculate the source of small POC, this parameter, the remineralization rate of small POC, is the only required parameter. So next, based on these parameter values, we can estimate the carbon export flux due to different mechanisms. And these figures show the time series and their mean vertical profiles. So based on these preliminary results, we can see that the blue lines, which represent a gravitational sinking flux of natural POC here, is the dominant mechanisms. And this conclusion can be also achieved from the other three float segments. But we can also see some differences between these float segments. For example, the green lines. So here the green lines represent the other export mechanisms of small POC apart from the gravitational sinking. So now we are doing more analysis. We are studying whether these differences is true variabilities or just come from the estimate uncertainties. Our next step is to apply this analysis in the South Ocean, where we have more BGC algal flows. So that's it. Thank you very much.